In this lecture, we look at some special thermodynamic processes, for example, isotherms, adiabats, etc. The first one we look at, we have seen before, is constant pressure. In constant pressure, you start at some initial state, and you go to some final state. On a pressure versus volume chart, it goes from the initial state to the final state is a horizontal line. The relationship is that the volume is directly related to the temperature, assuming that we have N and R and P are constants. The work done is just simply the pressure times the change in volume. Constant volume we've also looked at, and it's a vertical line going from initial to final states. The relationship between pressure and temperature is a direct one, where alpha is a constant, where the number of moles, R and V, are constants. The work done, of course, is zero because there's no area underneath the curve. Okay, a new idea is a constant temperature process, or sometimes known as an isothermal process, or the curve that goes along with it is known as an isotherm. So in this case, the blue curve going from I to F is an isotherm, and the pressure is related to the volume, where it's equal to a constant beta times 1 over B. So the curve is in 1 over B curve for the pressure. The work underneath that curve is given by the value, by the equation there. It's the N times R times temperature times the natural log of V final divided by V initial. And this can be found using calculus to find the area underneath the curve. An adiabatic process is one where the heat does not change. Q is equal to 0. So there's no heat input into the system. And that's this purple curve, and it's similar in shape to the isotherm, because when you look at the formula for it, the pressure is equal to a constant times V to a minus power. This gamma, the power, is the ratio of the molar specific heat for constant pressure to that for constant volume. So it's Cp divided by Cv. For an ideal gas, this ratio is 5/3. So it's not very far away from the one that you would have had the power for V for the constant temperature. Since there is no heat going into or out of the system, the work is then equal to the change in internal energy of the system. Let's look at an example of an artificial heart. This artificial heart is powered pneumatically. That is, the piston in the cylinder rises as the gas expands, pushing the blood through the exit. As the piston returns to its initial state, more blood flows in and is ready for another cycle. The entrance is not shown in the picture. The expansion is done under constant pressure. Then the pressure is reduced at a constant volume by cooling the gas to its original temperature, and then the compression stage of the cycle follows an isotherm back to its initial state. So if we look at the work done by the gas cylinder in the system on this cycle, we see that when we go from the states 1 to 2, we're a situation where the pressure is constant and the volume changes. So we have whatever the pressure is at 1, it's still at 2, so it's P1 times the difference between V2 and V1. That's the work done. On the path from 2 to 3, we're on a line which is at constant volume. The volume isn't changing, but the pressure is. But since there is no area underneath this vertical line, W23 is equal to 0. The return is along an isotherm, and we use the formula for the work for the isotherm, and it's just N times R times the temperature times the natural log of the volume at V1, the final volume, divided by the initial volume V3. And the total work would be then just the sum of these three components, so W12 plus W23 plus W31. If we go back and look for a second at each of the individual parts, we see that in W12, heat flows in and the temperature rises. In W23, heat flows out and the temperature falls. And W31, the temperature is constant. And if we add these up, the final result is this P1 times the difference between V2 and V1 plus this N times RT, natural log of V1 over V3. And that's the result.